In this video, we're going to go a little bit more in depth about probability density functions. We're going to start by considering the area underneath a probability density function. So if little f of x is our probability density function, I can use the fundamental theorem of calculus part 2 to evaluate the area under the curve. I just need to know its antiderivative. And lucky for us, we do. We defined the probability density function as the derivative of the cumulative distribution function. So that's why we've been calling the cumulative distribution function capital F and the probability density function lowercase f. We have our reasons, I promise. So if I'm not thinking of this as PDFs and CDFs, I just see this integral, I say, well, this is going to be the antiderivative and antiderivative evaluated at b minus an antiderivative evaluated at a. And again, because of the way we've defined the probability density function, the antiderivative is the cumulative distribution function. And we've seen before, if I take the cumulative distribution function and I take f of b minus f of a, provided b is greater than or equal to a, this is precisely the probability that our random variable is less than or equal to b, that's f of b, and greater than or equal to a. We've subtracted off all of the instances where it's less than a. So one really useful way to interpret the probability density function is as a function where if I take the area under the curve in a certain interval, that's the probability that the value of my random variable falls inside that interval. So let's take this little f of x as the probability density function of some random variable, and I've sort of conveniently told you the area underneath the curve of this little hump here and that little hump here. So given this information, it should be very easy to calculate the following probabilities. What are the odds that I choose some random number that falls according to this probability density function, and that number is between 0 and 1? Well, now we know that that's precisely the area under this curve from 0 to 1, and we are shown that that's 2/3. Why don't you take a second now, pause the video, and evaluate the remaining two probabilities. The odds of being between 2 and 3, as we just learned, are going to be exactly the area under the curve from 2 to 3, and we're shown that that's 1/3. And the odds of being between 0 and 3 are exactly the area under the curve from 0 to 3. So let's look here. 0 to 3 is under here. I've got an area of 2/3 here, plus an area of 0 here, plus an area of 1/3 here, so altogether that is 1. So this tells us that whatever this random process is, it always gives us numbers between 0 and 3. In fact, it always gives us numbers between 0 and 1 or 2 and 3, never any numbers between 1 and 2. Let's explore a little bit more this relationship between probability density functions and cumulative distribution functions. I know that the derivative of a cumulative distribution function, that is how we defined our probability density function. But what if I want to go the other way? If I want to anti-differentiate my probability density function, there's going to be a plus c. There's infinitely many different functions that have the same derivative, but I can use this insight here to figure out which of these is going to be my cumulative distribution function. Remember the definition of a cumulative distribution function, f of x. That's the probability that my event is less than or equal to this number x. And from this line above, I can see that is the improper integral from -infinity to x of my probability density function, little f. Now my variable here is x, which has already been used. So I need to come up with a new variable, t. So I want the area under my curve for all numbers less than or equal to x. Well, that's from -infinity to x. So if you have a cumulative distribution function You differentiate it to find the probability density function. If you have a probability density function, you take this improper integral to get the cumulative distribution function. Let's do a concrete example. Let's say this is my probability density function. So first off, I can use this just to find some very discrete probabilities, like we did in the previous example. Why don't you pause for a second? You should definitely be able to find these first two. You can also think about how to find the third one. We said that the area under the curve gives us the probability of being in that interval. So if I want to know the probability of being between -1 and 0, I just take the area under the curve here, which is 0. So for this random process, I never get any values between -1 and 0. What about the odds of being between -1 and 1/2? Well, from -1 to 1/2, I get no area here. And then here I get a triangle. I can see that this triangle has height twice as big as its width. It's similar to this large triangle that goes from 1 to 2. So if its base is 1/2, then its height is going to be 1. So the area of that triangle is 1/2 base times height, which in this case is 1/2 times 1/2 times 1, which is 1/4. So I want to know all the area under the curve from -1 to +1/2. From -1 to 0, there's no area. From 0 to 1/2, there's 1/4. So the probability that I run this random scenario, the probability that the number I get out of it is between -1 and 1/2 is 1 in 4. Now let's think about, in general, the probability that the number I get is less than or equal to some number x. I'm going to need a bigger screen. For this step, it's nice to have a good intuitive understanding of the probability density function. So remember what this looks like. If I were to run this trial a whole bunch of times and record the number I got every time, this higher value of my density function means it'd be more dense around here, and this lower number means it would be less dense. So these are all zeros, density 0. I never get any numbers bigger than 1. Density 0, I never get any numbers less than 0. And in here, the numbers I get are more densely clustered the higher I get. Right? Down here in this area, the y value of my probability density function is low, so I have a low density, not that many trials. But then as my x gets closer and closer to 1, my density function gets larger and larger, and so I have more and more values from this range of numbers. So let's go back to cumulative distribution function. I never get any values in here. So the probability that I get something that's less than 0 is 0. And in fact, the probability that I get something less than or equal to x is 0 if x is any number less than or equal to 0. So the probability it's less than or equal to -1 is 0, and the probability it's less than or equal to -2 is 0, and so on. So f of x, my cumulative distribution function, that's just the probability that it's less than or equal to x, is equal to 0 for any number I put in there that's less than or equal to 0. Now let's think about the other end of the spectrum, over here. What happens if I'm greater than or equal to 1? Well, every single trial is less than 1. The probability that I do my trial and it's less than or equal to 1 is 100%. They're all in this little range. So the probability that I do my trial and it's less than or equal to 2, well, still 100%. The probability that I do my trial and it's less than or equal to 3, still 100%. So f of x, probability it's less than or equal to x, is 1 if x is at least 1. So for everything in this range, my cumulative distribution function is 1. And as a quick review, this accords well with two things we know about cumulative distribution functions. If f of x is a cumulative distribution function, then the limit as x goes to negative infinity of f of x must be 0, and the limit as x goes to positive infinity f of x must be 1. This comes from the cumulative bit. So far, so good. Now we need to figure out what's going on in that pesky middle bit. So let's think about this middle bit. As we just saw, big F of x is the area under the curve from negative infinity to x of my probability density function. In this case, that's the same as the area from 0 to x, because there's no area to the left of 0. So if I'm in this sort of interesting middle bit between 0 and 1, and I want to know the area under the curve from negative infinity up to x, well, it's a big old 0 plus this triangle. And what are the dimensions of this triangle? Well, again, by comparing it to this large green triangle, I can see that its height is twice its base. So if its base is x, its height is 2x. So the area of this triangle, 1/2 base times height, is 1/2 times x times 2x, also known as x squared. Notice there's no plus c because this is a definite integral. I want this area. So now we can put this all together. What is my cumulative distribution function? It's 0 if x is less than or equal to 0. The probability of being less than 0 is 0. The probability of being less than -1 is 0. The probability of being less than -2 is 0, and so on. It's 1 if x is greater than or equal to 1 for all the same reasons. And if I'm asking the question for this sort of interesting interval here, it's x squared.